In this lecture, we want to take a look at a new ADT, which is the dictionary, and the most common or important implementation of dictionaries, which is a hash table. Dictionaries are nonlinear structures. That is, the structures we've studied in the course so far are all linear structures. They have a concept of adjacent elements that are processed in some fashion, for instance, for a stack or for a queue. But dictionaries aren't this way. That is, there's no guarantee about the way in which data is stored in a dictionary, and they're not designed for processing sequentially, in the sense that with the stack you pop from the same direction, and a second pop will always remove the one adjacent to the first pop. However, that's not the case with dictionaries. Also, dictionaries have two parameterized types instead of one. Your data takes the form of key equal value pairs. This is an important idea. The key indicates, points to, or is a way to find the value for the dictionary. Keys are distinct, that is, there cannot be any duplicates. And each key maps to a specific or allows you to find a specific value. We call these dictionaries, though the metaphor doesn't exactly fit. The metaphor sort of fits. For example, with a dictionary you have a word and you look it up, and what you find is the definition for that word. So in this instance, the key is the word you're looking up and the value is the definition that you find. The problem with the metaphor is that, in English at least, one particular word can mean more than one thing. For instance, you might say, take the word bank, and bank can be a place where you keep your money, or bank can be the ground at the side of a river. That can be a river bank. So here we have a situation where one key maps to two different values, but this can't be allowed or supported in dictionaries in the computer. Thus, you cannot have duplicate keys. Each one is distinct and it maps to a clearly defined and unambiguous value. Another example of this in the computer terms might be something like a student read ID. You can have records that are the same, values that are the same, but not keys that are the same. I taught a class a few years back where I had 3 students in my class with exactly the same name, first, middle, and last. However, each of those 3 students had distinct read IDs. So for a student instance, you can't have 2 students with the same read ID, but you can have 2 students with the same name. So this is the idea of keys and values. The key is the read ID that is used to look up or find the student record. And you may have matching records. You may have students with the same name, though they're not the same student. But you can never have 2 students with the same exact read ID. Dictionaries are designed to be high-performance structures, and they're designed primarily for searching on the key. And so they are ordered, or data is stored in the dictionary based on the key. Searches based on the value are typically not even supported, though they may be. But in the case where you try to look something up using the value, these operations are generally big omega of n. That is, big omega of n meaning it's going to be at least linear, but it could actually be worse than that. We also refer to these as reverse lookups. An example of this might be you have a dictionary and the key is the phone number and the value is the name. If they're stored in this way, then reverse lookups means you take a name and you find the phone number that goes with it. Or you take a student's record, a student name, and look up his read ID using his name. So these types of operations are not optimal, and they're generally a lot slower than the preferred method for searching, which is given a specific key, find the value that matches it. So that's the type of operation we normally want to use. And these are typically very, very fast. The idea here is that dictionaries perform very fast searches based on the key. So these are the type of data structures where you have large data sets and you must look things up quickly. A dictionary is also referred to as a map, and the Java API uses this term, a map. It is a newer or more common name. In the Java API, the original term was dictionary, but they changed it to map at some point. Either name is completely valid. So here are typical keys: phone numbers, red IDs, employee numbers, part numbers, item numbers. And keys are typically strings. So you might have a phone number that points to a person that has that phone number. You might have the red ID of a student. You might have an employee number. You might have a part number. You might have an item number. For instance, Costco has item numbers on all their products. That item number is the key that is used to look up anything about or having to do with that particular inventory item. Look up the price, for instance, for peanut butter cookies. You use the item number to find it. This is an example of a dictionary ADT interface. This is not the interface, but rather an example of an interface. So you may actually have slightly different methods in a dictionary, but these are in general what you have. A lookup to see whether or not the given key is in the dictionary. This becomes important because the question arises on how do you handle duplicates. That is to say, if you have a key X that's in the dictionary and you attempt to add another key X equal to the first one to the dictionary, how should it behave? So the contains method becomes important to check for duplicates. The add method, again, how do we handle the duplicate situation? What the Java API does is it replaces the existing value with the new value if you have a duplicate insertion. Thus, the first key value pair that you're inserted, the value disappears and is overwritten by the second value. And this is done without throwing an exception or any other thing. So the method I have here for add to the dictionary is different from the Java APIs. This must return false if it's a duplicate and abort the insertion. Then we have delete. So given a key, find the key value pair and remove it. Get value. This is a standard lookup. This is generally quite fast. Given a key, find the value that maps to it or is associated with it, or null if it's not in the dictionary. Get key, again, is a reverse lookup. You have the value that you're provided as the parameter and you find the key that matches it. And this is typically big omega of n. This is a very slow method compared to the standard lookup where you use the key and find the value. So notice that in this structure we have two parameterized types, the k, the key, and v, the value. Continuing with this, we have the size. Is full, is empty, perhaps. Is full becomes important because hash tables are generally implemented using arrays which can be full. And so this method is important. If you have implemented your dictionary using an underlying data structure which is never full or cannot run out of room, then you should always return false in this case. Clear zeroes out or empties the dictionary, returns the dictionary to an empty state, and then you have two iterators, keys and values. Now you may have different requirements for the iterators, but typically this is how it is done. The key iterator returns the keys in sorted order. The value iterator returns them in the same order as the key iterator. That is, if we take both iterators and run through them, each key in turn will match the next value that comes out. So if the keys come out A, B, C, then the values come out ABC with the values that match those keys, ABC. There are several common dictionary implementations. Associative arrays are very important, and you see these in languages other than Java. The big idea with an associative array is it's essentially syntactic sugar. That is, it's designed to operate and look like an array, but it's not an array. And the key in this case is used as the index, and this is typically a string. So you will have an array and in square brackets a string, and that is the key that indicates the value. We have hash maps, which are implementations of hash tables, and these are done either with chaining or with probing, which we will discuss later. And then we have tree maps, or trees, where data is stored in a binary search tree of some type. Common choices are red-black trees, B trees, N-ary trees, and perhaps AVL trees, though less commonly so. The difference between these two is as follows. With the hash table implementation, you have big O of 1 operations for insertion, deletion, and searching. This, of course, is the holy grail for data structures. There's nothing faster than big O of 1. This is a very powerful structure that is very commonly used in computer science. This is heavily used, so there's a great deal of importance on you understanding how these function. Tree maps, on the other hand, typically provide login behavior for insertion, deletion, and search operations. So these are somewhat slower, though the difference between login and 1 is not that great. That is to say, big O of 1 is faster than big O of login, but the difference is not really measurable. The tree implementations are useful because they keep the data in sorted order. However, the hash tables do not keep the data in anything even remotely resembling sorted order. So associative arrays are very common in other languages. You will find associative arrays in things like shell scripts, maybe JavaScript, PHP. And what you note here is that the index is actually a string. For instance, we have a color here, an array of colors, and the entry or the key is red, and the value is the hexadecimal triplet, the red, green, blue values that go with it. So in these examples, we have keys that might be stored as integers, but they're almost always stored as strings. And this is true in general for dictionary keys. For instance, if you see an item number on something at Costco, it looks like an integer, but typically it's not. They're almost always stored as strings. And the reason for this is twofold. First, you're not performing arithmetic on it. You're not going to add two part numbers together. That doesn't really make any sense. And the other important reason is for comparisons. So 0, 1, 2, 3 is equal to 1, 2, 3 is an integer, but they're not equal as strings. Usually, keys which are strings have a fixed number of digits in them. For instance, a phone number has 10 digits. A red ID has 9 digits. But if you have leading zeros, then if they're stored as integers, they no longer match. So, turning our attention to hash tables, the big picture is just this. You can find something quickly if you know where it is. Well, obviously so, but how is this important and how does it relate? Well, suppose we have an array as shown here. We create an array and it's got 1,000 elements in it. Now, if you think about it, what's the complexity, or the big O complexity class, of the operation to find a value stored at index 500? It should be obvious that this is big O of 1. So given the index, if you have the index and you know what it is, what does it take to look up an array element? Well, the answer is that lookup is virtually instantaneous, and it's big O of 1. I think it should be obvious that the size of the array has nothing to do with the amount of work required to locate that element if you have the index. So the question then becomes, does it take the same amount of time to find the element at index 500 if the array is size 1000, or the array is size 1 million, or even if the array is size 1 billion? And the reality is it takes the same amount of time to fetch the value at index 500 for all three of these array sizes. Just as an aside, this is what happens with an array lookup, and it's important that you understand that these square brackets here, these square brackets are operators. They are operators in the same way plus, times, minus, divide are operators. And the operation they perform is they find the element at a given index. They use this formula. The location of the element you're looking for is the starting address of the array plus the index times the size of each element. So with the index 500 example that we gave, it would be the starting address of the array plus 500 times 4, and it's 4 because each integer in Java takes 4 bytes. They're 32 bits. So the byte address of index 500 is calculated this way. So as you can see, there's nothing about in this calculation. There's no reference to the array size. It's irrelevant. And because there's no reference to the array size, because the input size of the array size, is not used, this is a big O of 1 operation. So if we can store our data in an array and we have the index, we can do the lookup in big O of 1 time. This is a great idea and is very helpful, and we use this in some fashion to implement our hash tables. However, there's certain problems we need to address. First, we need integer indices. Strings aren't really an option. Java doesn't allow the use of strings for an array index. Well, to get around this, it's possible that we can come up with a method for converting strings to integers. So you might, for instance, use ASCII codes. So here we have the ABC, and the ASCII codes for ABC are in hexadecimal 41, 42, and 43. So we could just take those and concatenate them together to make an integer, 41, 42, 43. Or we could go ahead and say A is 1, B is 2, and C is 3. Do this by subtracting 40 from each of them. So that would give us 1, 2, 3 for ABC. This doesn't completely solve the problem, though. So basically, any key can be represented as an integer. But even if you have integers, very often the range won't work. So as an example, suppose the key is a phone number, such as what we have here, 619-552-5151. This can be the integer value 6,195,000,000 and so on. So then we would have this as the index into our array. But if we do this, we need an array of size 10 billion for this index to be valid. So already we have a problem. Suppose this dictionary contains phone numbers for a town of 5,000 people. Then how much wasted space do we have in the array? We have an array of size 10 billion, but only 5,000 of those 10 billion entries is actually used. So virtually all of the array is actually wasted. Not a good idea. The other problem we have is arrays take big O of n time for insertion and deletion when the data is ordered. Of course, we have big O of 1 insertion at the end of an array, or we have big O of 1 deletion from the end of an array. But if you're not inserting the data at the end, then you have to shift, which means you're going to have a big O of n operation to shift or manipulate elements. And so to get a fast solution, we're going to have one that does not involve any shifting or movement of elements in the array. Again, as I mentioned, the goal here is to get the fastest possible performance, and it turns out that using an array to hold the data for a hash table can be used, and in fact we can do this and get big O of 1 time for insertion, deletion, and search operations. The solution to this problem is hashing. So we solve these problems by using a hash function or a hash method. A hash function takes a string key and converts it into an integer. It does this in a generic way. That is, any string key can be taken as input. Then you have this black box, which is a hash function, and the output is some 32-bit integer. So there's certain properties we want of our hash code method. We want to allow any string object to be used for input. The output, and we're talking about Java specifically here, the output is a 32-bit integer. And of course the range of values for 32-bit integers is given here, minus 2 billion something to positive 2 billion. Java does not support unsigned numbers, so a hash method may actually return a negative number. It's important to be aware of this because if we're going to use this return value as an index to an array, we can't have a negative one. But half of the numbers we get back are going to be negative, so we will need to deal with this problem. So any 32-bit integer can be returned. And then it's really important that the hash function return an even distribution of keys. That is, given some arbitrary string input S, all outputs are equally likely. That is, there's no bias. It's not more probable that an input will hash to a specific location than any other, that the probability of all outputs is equally likely. So the probability P of an input string mapping to a specific integer n is the same as the probability that it will map to the integer n plus 1. So they're all equally likely. The method must be repeatable. Given an input str, then the method will always return exactly the same integer. And it must be efficient. We should add that if objects compare as equal using the Java compare_to method, then they must return exactly the same hash code. And if the object implements the equals method, then equals must return exactly the same hash code. That is, if you have two objects A and B, and they are equal as determined by the equals method, then they must return the same hash code. The Java native method is given here. This is public int hashcode is the signature. This method exists in class object, which is the top level hierarchy. Thus you do not absolutely have to implement or override this hashcode method, but you should if you don't have a hashcode method available that's not in this upper level or top level object class. The reason is there really is no absolutely generic way of determining a hash code. The best hash codes can be obtained when you know something about the object you're hashing. The Java language actually implements this hash code by using the address for where the object goes in memory, and it turns out that this is a pretty good way of doing a hash code. However, it's not optimum because, again, there is no real way to use a generic solution for every type of problem. So this hashcode method that exists in class object should be overridden in the class of object that will be stored in the dictionary, but not in the dictionary itself. This is a very important point, and this is a point that students get wrong. Hash tables do not have hash code methods, period. The objects that are getting hashed, the objects that are being stored in the dictionary, will have the hash code method. So this hash code method is going to return any of the 32-bit integers, including negatives. And the hash table is going to call the hash code method to get this hash code and then transform it into an index. So what I have shown here is what actually goes in the hash table class. You call hash code, but you don't write the hash code method in hash table. So this is kind of analogous to using compare to. When you created your linked list, you did not write class linked list implements comparable. The linked list doesn't implement comparable. If you implemented comparable in a linked list, that would mean you were going to compare two linked lists to see if they're equal, or one linked list is bigger than the other. And that kind of a comparison really doesn't make sense, and it's not what you need anyway. What you want to compare are the items that are stored in your linked lists, not the linked lists. Similarly here, you call hash code on the items that you store in the hash table. So the hash code method never goes in hash table. If you have a string that represents your keys that you're storing in the hash table, then the hash code has to go in that string class, not here. But you call it. There's a separation here of the logic. The items that are going in the hash table has the hash code method. But in the hash table, you actually take this hash code and transform it into an index. The hash code method returns a 32-bit integer. There's a separation of functionality here that I want to call your attention to. You call hash code on the key object in the same way that you called compare to on the objects that were stored into your linked list. The hash code returns a 32-bit value, but you're not going to create a hash table of size 2 billion for every problem. That makes no sense. So on the key we get the hash code, but then inside the hash table, in this method here, this private method goes in the hash table. You retrieve the 32-bit key, and then you cut it down to size. You mod it with the size of your table, and you will get the integer index. So you have hash code in the object going in the dictionary. You have get index in the dictionary itself. A comment about this code: once we retrieve this hash code, it might be negative, and roughly half of them are negative. Well, we can't have a negative index to an array, so we use this bit mask, and we AND this. This is a logical AND. The effect of this operation in parentheses is it zeroes out the leading bit of the hash code that's returned and makes it positive. It isn't necessarily the positive version of the number that's returned, but it is consistent and fast, and what it does is it transforms all of the negative numbers into positive ones quickly and efficiently. So we now have this positive 32-bit hash code, and we mod this by the table size to get our index. So think about this for a minute. If the table size is 1000, that's the maximum number of elements that you can store in your dictionary. If we take a 32-bit number and mod it with the table size, what we're going to get is a sequence of integers that will map to and fit the table. So if the table is 1000 in size, using this mod operator, we're going to end up with a number in the range 0 to 999. If the table size is 10, we're going to have indices in the range 0 to 9. So this is exactly the range of indices that fit your table. The mod operator gives you exactly this range. So there's a problem we have sidestepped so far, and we need to go ahead and talk about it now, and that's the problem of collisions. So suppose that this key is a 10-letter string. So with 10 characters, there are 26 to the 10th possible values. So that's a large number of possible keys, yet the output space is much smaller. So here, 26 to the 10th is the key space. This is the possible variation or possible number of keys that you can have, the permutations. But 2 to the 32nd is actually the output space. This is the 32-bit integer output, and it's a much, much smaller space. So we have a very large number of values that are transformed into a very small set of values, relatively speaking. In other words, given this example, there would be about 32,000 keys for each 32-bit integer if we take all possible keys. So it should be obvious then that we're going to have multiple keys mapping to exactly the same integer index. Well, of course, you're not going to actually have 26 to the 10th power actual keys, but the implication of this is that you're going to have a situation where very, very different keys map to exactly the same hash code. It's going to happen. It's not only likely, but it's absolutely certain that it will happen. So you have a situation where you might have something like this. You have as a key John Smith and you get the integer 1234. And then you use William Jennings and you also get 1234. You have Sally Doe and that generates 1234. Or even just XYZ and that also generates 1234. Not only is this possible, but it's certain that it will occur. Collisions always occur. This is the difficulty that we have with hash functions. We are going to have duplicate indices that show up or duplicate hash codes. And we're going to have to deal with this situation in some fashion. So we have to develop a strategy to mitigate the problems that come from collisions. So again, a collision is the case where two very different keys are transformed by the hash code into a 32-bit integer, and both of these very different keys generate exactly the same hash code. Now, since we will be using arrays to store elements in the hash table, it should be obvious that you cannot store multiple things at the same location. It's not possible. You can only have one thing at each index. So we're going to have to deal with this problem. Mitigation takes two different forms, or there are different ways to approach it. First, you have to develop a very good hashing code or hash method that provides as even a possible distribution of the keys given some arbitrary string input. The next thing we want to do is make the dictionary larger than the maximum number of elements we expect. In other words, we're going to waste space so we can lessen the impact of collisions. And finally, we're just going to accept the fact that our best efforts to prevent collisions will not be successful. We will always have collisions, so we need a strategy that will allow us to handle these collisions and store multiple pieces of data at the same index. So we want to look at a few of the common hashing methods. And the idea is a simple one. We're going to take a string as input and we're going to transform it into a 32-bit integer for output, and we want to do this in such a way that all of the 32-bit outputs are equally likely. So there are different ways of transforming strings. The first is addition. This is an example. You might split the phone number into three pieces and add them all together. Multiplication, the idea is the same, but in this case you multiply the three pieces together. Folding, you add different parts of the key together and perhaps multiply those parts. There are others. Another common one is using XOR with various parts of the key. The best method, the most useful method, and the one that provides the most even distributions is typically the exponentiation. Positional notation is typically used when we refer to integers, but we can use this same idea with strings. Suppose we have the integer 1234. We can rewrite this as 1 times 10 cubed plus 2 times 10 squared plus 3 times 10 to the first plus 4 times 10 to the 0. In other words, 1000 plus 200 plus 30 plus 4. We can use that same idea with strings. A, B, C, D is equal to. So what we're doing here is subtracting 40 from each ASCII character. 41 here is the ASCII character for A. So we're transforming this actually into 1, 2, 3, 4 by subtracting 40 from the ASCII code. So here we have 1 times 10 cubed, 2 times 10 squared, 3 times 10 to the first, 4 times 10 to the power 0. So you can take a string and you can use this as a way to generate the hash code. There are dozens of different types of hash codes that are available. A great deal of research has gone into developing good hash codes. There are a lot of different ones. The best hash codes come about when you can take into account some aspect of your actual problem. So we can return to this example of the town with 5,000 people. In this case, we can make the following assumptions. We need to have a dictionary with phone numbers for all of these people. All numbers start with the same area code and prefix. So only the last 4 digits change. Well, we could use these last 4 digits as the array index, and then we won't have any collisions at all. We'll have 0 collisions because 2 people can't have the same phone number. So this way we'll have the index in our array with 0 collisions, but the cost will be we're going to have 50% wasted space. That is, we need an array of size 10,000 for 5,000 numbers. And so in this way, the indices are actually the last 4 digits of the phone number, and this is a fairly efficient and clean way of doing it. So this is a rare case. This doesn't generally happen. When you can develop a hash code where you can guarantee that you will have 0 collisions, this is called perfect hashing. This is almost never attainable. In general, however, some form of exponentiation is the best way to do a hash. It gives you the most even distribution of the outputs. So the hash code method goes in the class of objects stored in the hash table. I've said this before, but it bears repeating because it's often something the students get wrong. The string is almost always a key. In this case, you can just use the method that already exists in class string. That is, class string exists in the Java API, and it has a number of methods that have been written and provided. And in fact, the Java language designers have made the class string final to prevent you from extending it and adding things. You take it as it is. However, it does have a hash code method that's already written, and it does use the exponentiation method to get the 32-bit integer. So you can just call it. In some cases, you may have keys that aren't actually strings, but some more complex object. I've given an instance of this here. If this is the key, this my key object, then you have to put a hash code method in it, but you can do this by just calling hash code on the string identifier. So if the object is a string, you can just call this hash code method rather than writing your own. So I have a few charts here to show you distribution of keys across the key space using various hashing methods. So the goal, of course, is to have more or less even distribution of the keys across the entire index space. So for these examples, each dictionary is size 1000, and then we look to see how many collisions we actually have. So the ideal situation here would be to have 1,000 cells in our table, and each cell has precisely 1 element, or no collisions, and a perfect even distribution. Here's the multiply method, and it turns out that only 12% of the cells have any elements in them. Here we have 880 or 88% of this table is essentially empty. But this is not as bad as it seems. The worst case scenario, one cell has 67 elements, not great, but we do have a distribution of the elements that's decent but not great. The folding method is better. Here 35% of the data, or the table rather, actually has data in it. The largest entry here where there is data is 2 elements, and this is not a bad situation. This is certainly manageable. The worst case, 4 cells have 7 elements. So again, this is not ideal and it's not optimal, but it's not dreadful. It is certainly better than the preceding multiply method, but it's not ideal, but it's pretty good. Here's the exponentiation method. So 70% of the cells have elements in them and 30% are unused. But the worst case scenario is cells with 3 elements and there are only 20 of those. So this is really quite good. This is the Java native method. This is calling hashcode method on the data without writing your own. And in this case, the behavior is very similar to exponentiation, though it's somewhat worse. Notice 61 cells have 3 elements, but with the exponentiation method, only 20 have 3 elements. So you can do a better job if you know something about the problem. This is the behavior you get if you don't override the hashcode method in class object. Conclusions. Hash tables are dictionary implementations. Dictionaries use key-value pairs and are used primarily for searching, but they provide big O of 1 insert, delete, search operations. Tree dictionary implementations keep entries in sorted order, but hash tables don't. In hash tables, the data is ordered based on the hash code that comes from the key. Hash tables store elements and they're based on the key, so they're logically ordered in that fashion. If you need ordered data, you have to sort with a hash table. And again, we've said this several times, but it bears repeating because it's something students often get wrong. Hash code methods never go in hash tables. They go in the class, whatever the key is, that's where they go. Hash tables take a hash code and map it to an array index. Again, the analogy we have used, this is very much like using compare to in a linked list. You don't implement comparable in a linked list. You call or use compare to in a linked list. Well, where is the compare to method written? The compare to method is written in the class of objects that actually goes into the linked list, but it is not written in the linked list class. And the idea is the same here. The hash code method goes in the objects that are stored in the hash tables, but never in the hash tables themselves. So hash tables take a hash code. They invoke the hash code method on the key, take the 32-bit value that they get, and map it to an array index, usually with the mod operator. A collision is where 2 or more keys generate exactly the same hash code, which map to the same index. This is a collision. These are inevitable. They will always occur. And so hash code methods and dictionaries must be designed to work correctly and efficiently in the case where these do occur. So this concludes our introduction to dictionaries and hash tables. In our next lecture, we're going to look at ways that hash tables are implemented to deal with collision. There are primarily 2 ways that this is done. The first method is called probing, or open addressing. And with this strategy, what you do is if you have a duplicate, you go to the given array index and you discover that there's something already stored there, you move to a new location that's vacant. You can do this by sequentially marching down the array until you find an available slot. There are different strategies that can be used, but essentially there is a set of rules or heuristics you use so that if you encounter a cell that's not empty when you need to store something, you follow those rules to move to an available open space. So again, this is called probing. The second strategy, which is the more useful strategy, is called chaining. With chaining, what you do is create an array of linked lists. Linked lists can hold more than one thing. Therefore, if you have more than one objects that hash to exactly the same location, that's not a problem because you're going to store them in linked lists at that location. So you're actually going to have an array of linked lists, and each linked list can hold multiple items as required by the hash code that returns from the objects.